In this video, we discuss 7 points about polynomial functions that help us to plot their graphs quickly. Point 1. Graphs of polynomial functions are continuous and smooth. Continuous means that there are no breaks or jumps in the graph of a polynomial function. Smooth means that there are no sharp points or corners in the graph of a polynomial function. Alternatively, we can say that smooth means that every point on the graph has a well-defined gradient. And here is an example of a graph that is both continuous and smooth. Here is a graph which is continuous but not smooth. It's continuous because there are no breaks. It's not smooth because this point has no well-defined gradient. Here is an example of a graph that is not continuous. It is discontinuous. That's because it has jumps. There is a jump from here to here, here to here, here to here. The graph of a function is continuous if we can draw it without lifting our pen from the paper at any point. Polynomial functions always look like the first example, continuous and smooth. And the three functions seen here are y equals x cubed, a polynomial function, y equals mod x, and y equals x minus the floor of x. Point 2 involves the behaviour of polynomial functions for large positive and negative x, and this is sometimes described as the end behaviour. And the question here is, what does the general polynomial function f of x do for large positive and negative x, i.e. what happens as x tends to positive infinity and negative infinity? It's convenient to consider the behaviour for polynomials of even and odd degree separately. Here we consider polynomials of even degree, i.e. where n is even and n is the power of the leading term. And there are two subcases, the one on the left being where the leading coefficient is positive, that on the right being where the leading coefficient is negative. And the leading coefficient is the number that appears in the leading term. In the animations that we see here, the red arrow shows values of x increasing towards negative infinity. The blue arrow shows values of x increasing towards positive infinity. And we see that when the leading coefficient is greater than 0, then f of x tends towards positive infinity, both when x tends to positive infinity and to negative infinity. And we see that when the leading coefficient is negative, then f of x tends towards negative infinity, both when x tends to positive infinity and to negative infinity. And now we consider the cases where n is odd. In this case, when the leading coefficient is positive, f of x tends to negative infinity as x tends to negative infinity, and f of x tends to positive infinity as x tends to positive infinity. And when the leading coefficient is negative, f of x tends to positive infinity as x tends to negative infinity, and f of x tends to negative infinity as x tends to positive infinity. And here we see a summary of these four cases. On the left we have the cases for even n, on the right the cases for odd n. At the top we have the cases for positive leading coefficient. At the bottom the cases for negative leading coefficient. The dotted portion of each graph shows that we are not interested in the behaviour for small values of x. The graphs only indicate the behaviour for large values of x. For point 3, we look at the relationship between the factors and the zeros of a polynomial. Now, if we can factor a polynomial f of x into linear terms x minus a, x minus b, x minus c, and so on, perhaps with a leading coefficient a sub n, then when we plug a into f of x produces 0, so f of a equals 0. And similarly for b, f of b equals 0. And for c, f of c equals 0, and so on. And when we can factor f of x in such a way, then the graph of f of x crosses the x-axis at x equals a, x equals b, x equals c, and so on. And in this case, the numbers a, b, c, and so on are called the zeros of f of x. And here we have an example. This cubic polynomial can be factored as x minus 1 times x minus 2 times x minus 3, and we correspondingly see that the graph crosses the x-axis at x equals 1, x equals 2, x equals 3. Now, this quartic polynomial of degree 4, can be factored as x times x minus 1 times x plus 2 times x plus 3. And you will note that that isn't quite in the form that I supplied here, because the negative signs are missing in 2 of the factors. However, we can rewrite it as x minus 0 times x minus 1 times x minus minus 2 times x minus minus 3. And now we can see that the graph will cross the x-axis at 0, 1, minus 2, and minus 3. Point 4 involves the behaviour of a polynomial at zeros of odd and of even multiplicity. And the question here involves repeated factors. The factors shown in green are of odd multiplicity, because they have an odd power. The factors shown in red have an even multiplicity because they have an even power. And for the red factors, we say that a is a zero of even multiplicity, and for the green factors, a is a zero of odd multiplicity. And the important fact here is that the graph of f of x crosses the x-axis at a zero of odd multiplicity. So here we have a polynomial of degree 4, which can be factored into two polynomials of odd multiplicity, 2x plus 1 and x plus 2 cubed. And we can see that the graph does indeed cross the x-axis at each of the associated zeros, which are minus 0.5 and minus 2. On the other hand, if we have a zero of even multiplicity, then the graph of f of x bounces on the x-axis. It does not cross it. And here we see a polynomial of degree 4, which can be factored as x times x plus 1 times x plus 3 squared. And so we have a zero of even multiplicity at minus 3, and we can indeed see that the graph of f of x bounces on the x-axis at minus 3. It does not cross it. On the other hand, we have zeros of odd multiplicity at 0 and minus 1, and we see that the graph of f of x crosses the x-axis at those points, minus 1 and 0. For point 5, we discuss the greatest number of turning points of a polynomial function. And this is a question of how many times can the graph of f of x reach a local maximum or a local minimum. And here is an example of a graph with a local minimum, which is the point here at the bottom of the graph. And here is a graph with both a local minimum, this point here, and a local maximum, this point here. And in fact, the graph on the left is that of a polynomial with leading term x squared, which has degree 2. And we note that we see one turning point, and we also note that 2, the degree, minus 1 equals 1, which is the number of turning points that we see. On the right, we have a graph with a leading term x cubed, which has degree 3. And we see 2 turning points, and we note that 3, the degree, minus 1 equals 2, the number of turning points. And in fact, the pattern that we see with these two examples holds more generally. A polynomial of degree n has at most n-1 turning points. However, there are some details to be aware of. A linear polynomial of degree 1, such as 3x plus 5, always has 0 turning points. A quadratic polynomial of degree 2 always has 1 turning point, and for polynomials of higher degree, like 3, 4, 5, the polynomial has at most n-1 turning points, but it may have fewer than n-1 turning points. And so here we have some examples. On the left, we have the graph of y equals x cubed, which is of degree 3, and it has 0 turning points. On the right, we have the graph of x cubed minus 6x squared plus 11x minus 6, which is also of degree 3, and which can be factored as x minus 1 times x minus 2 times x minus 3. And this has 2 turning points, here and here. And here at the bottom of the page, we see a polynomial of degree 4, x to the 4 plus 1, which has 1 turning point, here. On the right, we see a more complex polynomial of degree 4, which can be written as x times x minus 1 times x minus 2 times x minus 3 plus 2, and this has 3 turning points, 1, 2, 3. Point 6. What is the effect on the graph of a polynomial of irreducible quadratic factors? And an irreducible quadratic factor is one which cannot be factored into linear terms. The expressions shown here in the red box are all irreducible quadratics. On the other hand, the expressions x squared minus 1, 2x squared minus 9x plus 4 are not irreducible quadratic terms because they can be factored into linear terms as shown. An irreducible factor never causes the graph to touch or cross the x-axis. So, for example, if we look at the graph of y equals x squared plus x plus 1, and x squared plus x plus 1 is irreducible, then we see that the graph does not intersect the x-axis. It does not touch or cross it. And if we look at the graph of y equals x minus 2 times x squared plus x plus 1, we see that the graph crosses the x-axis only once at x equals 2, which is due to the presence of the linear factor x minus 2. There are no crossings or touchings due to the x squared plus x plus 1 term. And further, if we look at the graph of y equals x minus 2 times x squared plus x plus 1 times x squared plus x plus 3, where x squared plus x plus 3 is another irreducible factor, then we see again that we only have one crossing of the x-axis, again at 2, due to the linear factor x minus 2. The two irreducible factors, x squared plus x plus 1 and x squared plus x plus 3, cause no crossing or touching of the x-axis. Now, you may have noticed that both of the graphs on the right have turning points, and you may wonder if those turning points are due to the presence of the irreducible factors. The answer to that question is no. The presence of an irreducible factor does not imply that the graph will have turning points. On the left, we have the graph of y equals x minus 2 times x squared plus x plus 3, which crosses the x-axis only once, and it has turning points. On the right, we have the graph of y equals x minus 2 times x squared plus 3x plus 8, This graph crosses the x-axis only once due to the x minus 2 term, but in this case it has no turning points. So we see two expressions, both with an irreducible quadratic factor, but one has turning points and the other does not. So we can deduce nothing about turning points from the presence of an irreducible quadratic factor. And in fact, the only reliable way to determine if a graph has turning points is to use techniques from calculus. And finally, point 7, how do we find the y-intercept of the graph of a polynomial f of x? And this answers the question, where does the graph of f of x meet the y-axis? Well, this is pretty straightforward. The graph of any function meets the y-axis when x equals 0. So the value of f of 0 gives the displacement of the y-intercept. So for example, here we see a graph. We have the line x equals 0, which defines the y-axis, and we see that f of 0 equals 1.5, which is the displacement of the graph when it crosses the y-axis. In other words, it's the displacement indicated by the red arrow shown here. Now, for the general polynomial function, f of x is given by this expression, and so f of 0 evaluates simply to a sub 0, the constant term. And so we have a very simple result. For a polynomial function, the displacement of the y-intercept is given by the constant term. And here we have some examples. We have a linear polynomial with constant term 3, and we see that f of 0 equals 3, which is the y-intercept. We have a quadratic polynomial x squared, which we can write as x squared plus 0 with constant term 0. We see that f of 0 equals 0 and the y-intercept is indeed 0. We have a cubic polynomial x cubed minus x squared minus 5 over 2 with constant term minus 5 over 2. F of 0 equals minus 5 over 2, and we see we have a y-intercept of minus 5 over 2, or minus 2.5. Finally, we have a polynomial written in factored form with factors x minus 1/2, x plus 1, x minus 2, x minus 3. And we can find the constant term by multiplying all of the constants from each linear term. So we have minus 1/2 times 1 times minus 2 times minus 3, which evaluates to minus 3. And so we have that f of 0 equals minus 3, and the graph does indeed cross the y-axis at minus 3 as expected.